All right, guys, it's 2 o'clock. We'll get started. It's a continuation from yesterday. So I'm Venkat Raman from University of Michigan, if you guys forgot. So we were talking about large area simulations yesterday, how we do computational modeling, right? There are a few things that you're all going to do research, and you're all going to get a PhD. It's hopefully, right? So one thing you have to keep in mind, you have to know all these basics. This is all the stuff that has been done before. This is knowledge within the combustion world. But if you have to do research, you have to come at it with some angle that's your own, right? You cannot say, Ed Law did this or Ron Hansen did that, and so I'm going to do the next small thing from it. That's not very useful. So you have to somehow change the perspective, and that's how you make a name for yourself. This is very important, right? Yeah. But you have to figure out how to move away from what we do right now to think of some new direction. That's very important, right? So what we will do now is to disentangle ourselves from all of this prior knowledge by slowly figuring out what is wrong with each one of the assumptions we made, how things break, and so on. And by the time we finish the lecture today, you will no longer think LES is the next best thing, okay? And tomorrow, we'll start with the next best thing, which is high-speed flows and detonations and new physics, right? So this is like the middle, the second installment of a movie, which is never the most interesting part, right? So it's always the last installment that's good, if you stayed for the last one. So we want to talk about this. So first, to begin with this, you have to know what is combustion modeling in LES. That's what we're going to look at, so maybe for 1.5 hours or so. Then we're going to talk about some concepts that are outside of combustion, outside of fluid mechanics. Things like black swans or dragon kings. Do you guys know these terms? Okay, you see? So that's after, 2:10, about 3:30 or 4 o'clock, okay? So stay awake, don't fall asleep on me. So we'll start with combustion modeling first. We have to understand what is it that we're modeling and what are the failings of what we're trying to do, okay? So I will write this equation. I don't expect that you remember everything we talked yesterday, okay? I can go back to the previous slides if you've needed, but we are going to solve, this is way too high for me. So the top equation there, that's a tiny pointer. The top equation is the conservation equation for species. Is this equation correct or wrong? Wow, never been there, more silence. What do you think? Right or wrong? Yeah. So if I add all of these equations, sum over alphas, it will not give me continuity equation, okay? So always remember this. To correct this equation, I need a correction velocity called the corrective diffusion velocity, okay? If I don't add it, you cannot get continuity equation back. For the purpose of what we are trying to do, that term is not very critical, let's say, so I'm just going to write it this way. But typically, there's an extra term at the end, which looks like a convection term that corrects for that error introduced by multiple diffusivities that you have for the species. Now, what I can do is I can use the same principles that I used for LES yesterday for momentum equations, and I can filter those equations, right, this top equation here, and I'm going to get this equation at the bottom, okay? Now, unlike the momentum equations, where the only term I needed to model was UI uj bar, right? So that's the term I need to model, because I said if you multiply two signals and you filter them, it's not the same as first filtering the signals and then multiplying them, right? So that it's called commutation error. So that's what you have here. So instead, I need to model this term here, which looks very similar to the term that appears in the momentum equation. Instead of UI uj, now you have uj y alpha and tilde over it, because it's Favre weighted filtering. So I do need a model for this. We'll come to it in a second. But the most critical part is the guy on the right-hand side. So that's the chemical source term, which if you attend Professor Karan's lecture, this is all chemical source term, right? So that's the chemical source term, the most important thing for us. And now the chemical source term is filtered, okay? And this introduces perhaps the biggest challenge for combustion modeling in LES. Now, the chemical source term, if you think in terms of scales, is going to be active at a very small scale because reactions are confined to a very small region. So in terms of length scales, it's at a very small scale. If I say I filter that source term, I'm essentially saying all the contributions at the small scales, I'm going to set it to 0, okay? Which means there is no chemical source term after that because everything is at the small scales. So if you follow that logic, filtering that source term is the end of this whole exercise. Once you do this equation is meaningless. You cannot solve it. There's no point in doing LES or for combustion, okay? So we have to find a way around it. Just directly filtering the equations like this is not the solution. And I'll explain this in the next few slides using certain examples so you sort of see what the mistake we're making is quantitatively. So first for that pesky UJY alpha term, which I'm going to write like this. So if you remember from yesterday, that's how the subfilter stress term looks like. So it's very similar, and I can use these kinds of models. These are called gradient diffusion models, and there are, some people think it's good, some people think it's bad, but nobody has done anything better than this to this point. So we'll assume that it's a good model. So we can use this. This is not critical for us. It's important, but not a critical modeling requirement here. So we'll keep it at this level of exposure for this term. What is more critical for us is the chemical source term. Okay, and of course, you guys know this. All of chemistry, if you want to model it, fuel does not become carbon dioxide directly. There are multiple steps, right? We know multi-step chemistry, right? Okay, all right. Okay, we know multi-step chemistry. So we have a chemistry mechanism, and if you can use Cantera or you can use Chemkin or whatever software you have to read in a file that someone like Professor Karan or Hai Wang or others give you, and then or you're the ones developing this if that's what your PhD research is on, and then use it in a CFD calculation. Okay, so we're not talking about multi-step chemistry. This is only for illustrative purposes. So I'm refining that to a single-step chemistry. I have C and D reacting to give E and F. Okay. So you can think of it as fuel and oxidizer giving two products. And I'm writing that chemical source term for C to look something like this. So it's a product of the concentration of C and D. So square brackets imply concentrations. And then you have this pre-exponential factor, which has that A term, that's the A term. And then you have this exponential term here, minus EA divided by RT. So because of this, there's a dependence on temperature that's not linear. It's quite complicated. It's highly nonlinear. And so any linear approximation to the source term will not work. So you need to account for this highly nonlinear function in whatever calculations you do. So if I filter this function, I can write it like this. I've not done anything significant here. In fact, this tilde doesn't look very right. The tilde should extend over the entire right-hand side. I do not know how to make the tilde. So it just looks like a small one. It's over the entire thing, right? So you have the product of E power minus EA divided by RT, concentration of C, concentration of D. All three of them multiplied together, and you're filtering that signal. And that signal is most active when that temperature is high, right? That's when the reactions are very high, source term is very high. So it's going to happen in a very thin region close to the flame. Everywhere else, it's relatively zero or very close to zero. So when I filter that signal, that very high frequency pulse you get right at the front gets wiped out. So there's nothing left, okay? So that's what that filtering literally implies when you write it like this. So in a simulation, this is what it will look like. This is, again, example. I think it was done in 2003 or 2 or something like that. This is from Heinz Pitch and Matthias Immer, I feel. I'm not sure. I don't know the source exactly. I got this from a slide that he gave me, so I don't know the exact origins of this. So what they did was this. They took a homogeneous isotropic turbulence, a periodic box of some size, initialized blobs of fuel and oxidizer in it, So some blobs are fuel, some blobs are oxidizer. It's unity partition, which means that together they fill up the whole box. And at the interface between the fuel and oxidizer, they introduces this high temperature kernel. So that's why you see those bands there. Those are the high temperature kernels, okay? This is only the fuel and oxidizer, and then the box contains turbulence. So there's an initial condition that's very turbulent. And then you solve Navier-Stokes equations like DNS completely on this, okay? No modeling, no LES. It's purely for getting data. So this is DNS, and that's the left-hand side, okay? So in the middle, you have this plot where the temperature, theta here is temperature, which is an oddball notation, but theta is temperature. And the x-axis is tau, which is the time over which the simulations are done. And you see the tilde on top of that. That indicates some kind of averaging. In this case, it's not filtering, it's literally averaging. So theta here is the average temperature in that box, okay? So at this initial condition, there are certain parts that are very high temperature, the narrow yellow bands, they're very high temperature. But the rest of the domain is very dark, so there's no high temperature there. So if you average all of this, you'll find that theta is like 0.1, some normalized value. That's what it is, okay? So that's the average temperature. Now, as time evolves, okay, if this reaction catches up, if the flame catches up or the box catches fire, that temperature will go up, okay? And so you calculate the average temperature in the box, and then you see how high it goes, okay? So I'll run this simulation. Again, it's always a mystery whether it will work or not. Yeah. So the turbulence is wrinkling that front, everything is mixing, and you see that the whole thing now is burning. So it caught fire. So what I do on the right-hand side is I track these lines. Forget about flamelet closure assumption. That's Heinz Pitch's model, so he's trying to show his model is very good. But that's not our focus here. Look at the curve that says DNS data. That's a solid line here, okay? And the DNS data is this box. You take the average temperature and you follow it as a function of time, and you see that it keeps going up, okay? As it should, because it's catching fire. What you don't immediately notice is this flat line here, okay? And the flat line makes the assumption that the filtered chemical source term is the same as the source term obtained using the filtered Y value. So you first filter the compositions, you compute the source term using these filtered values, and if you do that, that's that flat line you get. So essentially the flat line tells you, if you make that assumption, you get no reactions at all. So combustion does not exist. So this is the fundamental issue. In the previous slide, if you look at the equations you have, I'm going to solve transport equations for C. That will be Y1, let's say, and D, which will be Y2, Y alpha, so alpha is 1 or 2. I'm going to solve transport equations in LES for filtered Y and filtered Y2, filtered C and filtered D. So if I want to compute this chemical source term, if I know the filtered temperature and the filtered Y and filtered T, I can plug all of this to compute the chemical source term. So that would be first filtering the signal for composition and then computing the source term, which is a very nonlinear function. And it turns out that that gives extreme errors. If you do this, you don't get any combustion at all, okay? So this is the fundamental problem with combustion modeling. So everything that comes after this is a way to fix it. Somehow we need to fix this fundamental issue. And there are many ways to fix this, and people have come up with many different ideas. And there are a sequence of ideas for this from things that have been done even before LES was formulated for other kinds of simple mathematics or simple models, all the way up to more extremely modern technologies like if you have the filtered signal for composition, can you use neural networks? I hate saying this, but using neural networks to figure out the filtered chemical source term, right? Stuff like that. So that's this correlation that you can try to get. So there are a lot of ideas that have been pursued like this. So we'll go through one or two, and then I'll tell you what's the more dominant way to solve this that actually makes sense. So the easiest way to do this is this. You say that the filtered source term is evaluated using the source term of the filtered variables, which does not work out, so that's not an obvious choice. So I can come up with expansions, like Taylor series expansions. So instead of having T as being T filtered or T average plus T prime, I plug it in, and now I have a completely different expression for how to compute chemical source terms, or in this case, temperature source terms. That's a little bit more complicated, but it takes into account the fact that there is not a single temperature, but it's a filtered signal. Yeah, so you can make these assumptions there. What you'll quickly find is that these methods are not extensible. That works only if you have a single-step chemistry. If you have more complex chemistry mechanisms, if you want to predict pollutants or soot formation, for instance, these will not work. So you need to come up with something that's more principled. In machine learning terms, this is called physics-inspired modeling or physics-informed modeling, right? So you have to know something about the physics of the flames, and you can incorporate this into the simulations, and that way you're closer to reality than just doing mathematical expansions. And there are many classes of methods. In fact, many of the people who give these summer school lectures, if you go back and look at them, they're all associated with this. They would have come up with one of these methods. Okay, this is a path to glory if you're a combustion researcher. You come up with your own combustion model, and then, of course, you don't name your own combustion model after yourself, which is looked down upon. But otherwise, you can, they would have built this one. So, for instance, the flamelet methods, which fall under manifold-based methods, Norbert Peters and Foreman Williams came up with this technique. There is the conditional moment closure with Bob Bilger and Alex Klimenko derived. I do not know where the eddy dissipation concept comes from. It predates all of LES. The transported PDF methods come from Steve Pope and originally from others in turbulence field. And these are all only when you have diffusion flames or non-premixed flames. If you have premixed flames, there's a whole another group of researchers who do this stuff. And so there are manifold-based methods. For instance, Luc Verwisch builds these methods. You can have things based on reaction progress variable or thickened flame models, which Thierry Poinceau built, and they made it popular. And then there are flame surface density and G equation approaches, which there are many different authors who work on this, right? So there are techniques that are derived knowing that you cannot close that chemical source term. And there's always the same routine for this. And one way you can make a mark is if you come up with a new way to describe the flame structure, right? So these guys have thought of a certain way to do this. These are not the only ways. You can come up with multiple ways to do this. And that will provide an entry point into figuring out how to model flames within this large area simulation concept. Now, you have to know that diffusion flames are more popular for aircraft engines because their fuel and oxidizer are put in separately into the combustor. And premixed flames are more common in stationary gas turbines. And I don't know the history of this, but for some reason, in this country, diffusion flames are studied more commonly. And in Europe, premixed flames are studied more commonly. Not that they don't look at diffusion flames or we don't study premixed flames. It's simply that if I look at these methods, the people who build the methods are either from the US or from Europe. It's like that, right? So that's what you see from this. Yeah?
Why actually diffused flames are more common in aerospace industry? Why they won't use any premixed?
In aircraft engines. So if you mix fuel and air and you let it sit in any volume for appreciable time, it's dangerous, right? And aircraft engines have to be compact because volume and size are limitations. So you cannot have extra measures to ensure safety very easily. So the better strategy is to bring them in only when they need to react. In stationary gas turbines, you can have additional measures to protect or mitigate these risks. And so they can be longer volumes, things like that. And so as a result, they operate in premixed. Now, there's also a secondary thing, right? Diffusion flames produce NOx. Premixed flames can be run very lean, and they don't produce NOx. And because premixed flames in stationary gas turbines sit on the ground, you do not want to release NOx at ground conditions, which can be very detrimental to the humans. Not that we can release at high altitudes NOx, but that's what we do, that's what we do.
Models for the flames. Is there any way to couple them, or is there any model that can take care of triple flames or any sort of intermediate flames?
Yeah, so although I say as if there's a stark distinction that aircraft engines are purely diffusion flames and gas turbines are purely premix flames, stationary, that's never the case. They're always somewhere in between, right? It's simply the stationary gas turbines are more towards the premix side, and aircraft engines are more towards the non-premix side. For your question, that's the bottom one. Stratified and partially premix flames are the typical norm. And so there you have a variation. If it's a premix flame, you have variation in equivalence ratio throughout the geometry, and so that's stratification. In partial premixing, you have some amount of maybe products mixing with fuel-air mixtures, things like that, and they will lead to structures like triple flames, lifted flames, and so on. Then it becomes very murky. We don't know how to deal with it, and what we typically do is there's some ad hoc way to extend the premixed or diffusion flame models. We have gotten much better at it, so now the manifold methods we talk about can cover a broader range. I'll show you some examples. But it's not a settled question. It's not like we know, okay, if you do this, you can solve those problems. Any other questions?
Just broadly speaking, are the combustion regimes and rocket engines for this discussion pretty much similar to that of a jet, or are there other?
Yeah, so they're fully non-premix. That's right. Yeah, they're all mixing limited scramjet engines. They're all roughly the same.
Is there any notion that if the fuel and air, or in rocket, when we take in our rocket engine oxidizer and fuel, if we mix properly before the combustion, then the combustion will happen properly and emissions will decrease? Is there any?
Yeah, so ideally, if you can mix everything properly, and you can also burn. I mean, I'm not trying to trivialize it, but this is our thinking, right? We think if we mix properly and we can burn it well, everything will be perfect, right? But our limitation is fluid mechanics. So if you try to mix properly, which means fully mixed, not only that, you will lose, there'll be consequences for it. There'll be pressure losses. You need bigger volumes, so it may not be compact. So this is an engineering design. If you had infinite, capacity to deal with some problem, then perhaps we can design things like this. But in an engineering setup, you're also fighting against, making the whole thing reliable, stability, performance over wider operating conditions. So to ensure that everything works out at the same time is impossible, right? So it's always an optimal condition, but not, one ideal condition.
So diffuse flames will have higher emissions?
Diffusion, depends. If it's NOx, NOx relies on temperature. And in a diffusion flame, there's always one location, like what we saw in that movie, where stoichiometric conditions are present, so they'll have the highest temperature. So if that persists long enough, then NOx formation gets promoted, so there'll be more NOx. But in gas turbines, to have stability, there's always a pilot burner that sits in the middle. And that pilot is typically a diffusion burner. So that produces the most NOx in the entire gas turbine. So it depends, yeah. Anything else? Yeah.
For the conditional moment closure, I know there have been extensions with conditional source estimation, which have been used for premix flames. So can you just touch a little more on that, on how they've been kind of varied to work on premix and partially premix?
So to me, so there are only two. So it used to be. I mean, this is the history of how I learned it. Okay, there were three legs to the combustion modeling world, three legs to the combustion modeling stool. There was flamelet methods on one side, PDF methods on the other side, And then this conditional moment closure, which is considered the third leg of this. But if you look at the math of it, conditional moment closure is somewhere in between flamelets and transported PDF. You can derive a large part of it using the same techniques. Conditional source term estimation is an extension of that concept to LES because you can, because you have more access to the fields, you can back out the source terms and so on. There's always pros and cons for every method. And science, and you will realize this very quickly, really depends on the people working on a particular topic. If more people work on flamelet models, now flamelet models will be made more perfect, and so we will think it's a much better solution, even though perhaps conditional source term estimation is better, but not many people work on it, right? So there's nothing particularly negative about source term estimation or positive. It's just one other way to represent it. Not a very convincing answer, but yeah. Anything else? Yeah.
Well, a stirred reactor model is also considered as a premix calendar.
So in a multi-zone model, you take the combustor volume and you can split it into different zones. Is that what you're talking about? Yeah. And then in each zone, you will have like a perfectly stirred reactor or imperfectly stirred reactor, and they're all connected to one another. Yeah, there are many such models that are there. But in the context of LES, there's only a few that are used, so I'm only listing those. But there are many such variations to that, yeah. It's what you do within each stirred reactor. If you assume they're imperfectly mixed, then they become more like diffusion flames. Otherwise, they are more like premix flames if they're fully mixed. All good? Okay. So we cannot possibly look at both of them. That's not, I don't want to go through 1 hour of diffusion flames, 1 hour of premix flames. I want to only look at the concept of how we do the modeling, and then I trust that there are papers you can read and you'll figure out the rest of it. Yeah. So that's what we're going to do. I'm particularly fascinated by manifold methods, simply because I'm, like I was saying before, I'm more exposed to the people who work on manifold methods. Heinz Pitch taught me combustion. He works on this stuff, and so I've naturally learned from this. My PhD advisor works on conditional moment closure, but it's been a while since I worked with him, so I forgot all about it. So that's part of it. Yeah. So we'll look at manifold methods because they're critical for the discussion we're going to have later also. And they bring out a particular aspect of flames that we need to understand. Whenever we think of combustion modeling, we're thinking both chemical reactions, heat release, stuff like that, but also the fluid mechanics. And a lot of people who study fluid mechanics and turbulence and CFD, when they start doing chemical reactions, they come at it from the fluid mechanics background. So turbulence is important. We need to filter it. How are you going to model the source term? Things like this, right? But it turns out, if you come from the combustion side, it's vastly different. Combustion heat release is so dominant in all of these processes. The thermodynamics of combustion really dictates what the fluid would do. And that part is often missed. So most of CFD and combustion modeling comes from the fluids background, which is why we are looking at it this way. We take momentum equations, we filter it. Like, if you do combustion, we won't care about momentum equations first, right? So that's the part I want to think about, like the idea that the thermodynamics of the flames really controls how the flame structure looks. And if you think about it from that point of view, maybe there are new ways to model it that we have not thought about before. So that we will look at it in the second part of it. So to start with this, you really have to understand a little bit of statistics. I don't know how many of you took any statistics course at all before. Have you guys learned statistics? Like, what is a distribution function, like a PDF? You guys know what a cumulative density function is? Okay. You know what a 2.2 time correlation means? Okay. No, I was just making it up. That's not. That's not what I care about. So let's say we take a distribution function. That's the only thing we need for this. So distribution functions are essential for sort of understanding, given some data, how are we summarizing? These are called summary statistics, right? We are trying to take all the data, let's say Excel spreadsheet, and instead of just giving that Excel spreadsheet to someone else, we are condensing that information into some useful quantitative metric, and then we transfer it, right? So instead of giving the entire data, I can say, oh, don't worry about it. All this data is Gaussian distributed with this mean and this variance. So if I say this, it's 2 numbers and 1 word, like Gaussian, that I have to give to somebody else, rather than the entire Excel spreadsheet. So that summarization is what statistics does, right? And so we want to use this to model combustion, and that's what we're trying to do here. So the best way to think about it, again, I show these kinds of snapshots all the time. You can think of this as one filter volume, a delta of size delta, and inside the delta there are scales up to eta, Kolmogorov length scale, of scalars that are being distributed. They're spread all around it. So if I look at if I take a snapshot with the size of delta at any given time, I'm going to see this picture on the left. So I take all those points, and this is some scalar value, so it goes between 0 and 1. Think of it like mass fraction. At each one of those points, there's a separate mass fraction. I take those numbers, I put it in a list, and I construct a histogram, and I normalize this histogram, so which is when I get the picture on the right. So on the right, the x-axis is that scalar value, so it goes between 0 and 1. And the y-axis, there's no limit to it. In fact, if it's truly just a single value there, no distribution, just one value, the peak of the distribution will be at infinity, okay? So it's not that y-axis is count number, so it's very different. But I'll get this distribution. This is what I call a PDF, or a probability density function, okay? So I get this PDF, and this is the basis for everything that I'm going to do. Now, I can do this for temperature. I can take temperature distribution like this, construct a PDF. I can take velocity and do the same thing. Or I can take velocity, take its gradient, right, in x direction, let's say, and then construct the same data. So all I need is a field of values, and I can construct a histogram or a normalized histogram out of it, which is what I have for this PDF here. Okay? So this is important. So I first have a PDF. So everything I'm going to do after this is based on this PDF. So if I take this PDF, it doesn't have to look like what I plotted before. Depending on where I put that box and collect the data, that PDF is going to look different. So there's the red line, the green line, and the blue line, and they're all different because I put the box at different locations. I collected the data within that box, and then I do the PDF, and I get different values. Okay? So if the big box now is my integral length scale or domain, and the small box is my filter volume, as I move that filter, my PDF will change. So I'll have a PDF in every location that's a little bit different. So the PDF itself is not a single function that I have. It's a function. It's a function that varies with space and time. If I take this at a different time and I plot it at the same location, I might get a slightly different PDF. Okay? So now I have a PDF, which is a function of both space and time. And that PDF itself is a function of the y alpha or the mass fractions or whatever else you're plotting, right? So every PDF now, in the simplest form, let's say in one dimension, using one scalar, and in time, will be a function of the scalar, the position, and time, so it's three-dimensional already, okay? So the PDF is a three-dimensional function for a single scalar and one dimension. If now I have 25 scalars, like I have a chemistry model with 25 species in it, so then I'll have PDF that will have 25 variables next to it, and then one space and one time. Now, if there's 3 dimensions, there'll be 25 variables, then x, y, z, and then time, right? So it becomes 29-dimensional PDF. So the function blows up very quickly, right? So we can think about one-dimensional function. If I say y equal to x squared, you know what that looks like. I can even say things like x squared plus y squared is equal to 1, and you know that's going to be a circle, right? Yeah? Okay, all right. You know that's going to be a circle. But if I say there's a 29-dimensional function, how are you going to think about this? There is no, we're not capable of doing that. But that's what this gives you. This is how I want to construct this. So keep this in mind. So if I have 25 species, I'll have this. Now, Professor Karan has mechanisms, chemistry models, that might have like 1,000 species or 1,500 species, whatever it might be, right? So then this PDF is 1,500 dimensions plus 3 space plus 1 time. So it's 1,504 dimensional function. Okay? So this we have to remember, a PDF. Now, different people think of it differently. To me, conditional moment closure, transported PDF, manifold, they're all the same. They make approximations for what is the structure of your flame at different places. That's the only difference. So everything starts with that PDF that I just explained to you. And that's what I've written at the top, okay? So I have this PDF P, and it has an argument psi. So I have to use a lot of Greek symbols and letters here because there are too many things, right? So that's psi. And that psi itself is a vector, okay? So it has n species. So that n could be like 1,500 if you have 1,500 species. It could be typically when we do simulations, these mechanisms have 10 species or 25 species, things like that. So there are, so n is going to be like 25 in a common simulation. Nobody's doing simulations with 1,500 species. Right? That's not what you do. So that's your n in that psi, okay? And then I have this PDF. Now this PDF has certain properties. You remember I took this PDF from a single volume, okay? Which means I took all the data from that volume. Now if I take all the data and I find the average of the data, that will give me the filtered value. This is the definition of a box filter. So it will give me the filtered value. In PDF notation, I write it as a second formula, phi tilde, which is my filtered species, let's say, is the weighted average of psi times that PDF. So this is the definition of a PDF. If you want to find the mean of the distribution function, you weight it by the variable, you do the integral, and what you get is a filtered function. Okay? Now, if you haven't seen this before, this is not so obvious. It's not like, I can say this, and it's not like d dx of x squared. It's not like this, right? So if you haven't seen this before, you just have to, blindly trust me that this is the right formula. And you can verify it later if this is actually true. But this is what you get. So you can write your filtered variables using this PDF, okay? Now, of course, the PDF itself I got by taking the data and then constructing it. So what's the point of doing all of this and then saying I'm going to get the filtered value? It doesn't make sense. So the value in writing it as a PDF is to be able to write an equation for the PDF itself. So you solve and for the PDF itself, and then once you solve it, then you can find the filtered species or whatever else, to temperature or whatever else you want. So that's what you would do, okay? So the methods that we have here, they're all based on how you solve for this PDF, okay? So if it's a transported PDF method, which is what Steve Pope made popular, you directly write a transport equation for P, and then you would solve it. It's complicated. We'll come to that later. It's not some easy thing that we think about. It's a complex equation. You cannot use CFD in the traditional way. You need what are called Lagrangian methods for it. So it's a Monte Carlo method. So it's a very different approach altogether. But that's one way. The complete extreme of the other way is the last one, the manifold methods. In the manifold methods, we make a very simple approximation first. We take that psi, which is the vector of variables, and we split it into two parts, psi r and psi m. So the union of those two variables is the full variable set psi. Psi r, the subscript r, refers to reactive species, let's say, and the subscript m refers to manifold variables. And I'll come to this in a second. But essentially, you take the original set and you construct this new set. Now, it's not necessary that psi r and psi m are directly those variables psi 1 through psi n. You can do some manipulations. You can recast them in different ways and so on. But ideally, you split that original set into some small set psi m and the leftover set psi r. Okay? And what you do is you assume there's a relation between r and m variables. And that relation is your combustion model. Flamelet models or equilibrium models, Burke-Schumann condition, they're all the same. They're all this relation between the r and m variables. Once you have it, you do not now care about the PDF for the psi r variables. You do what is called marginalization of the PDF. And you only care about the PDF of psi m, the manifold variables. So if you had 1,500 species, you will have maybe 2 manifold variables, and perhaps the rest of it is all reactive species. So then you only solve for the joint PDF of those 2 variables, and you can figure out the rest of the variables, all the other species, just from these 2. Okay? So that's the power of what the manifold methods can do. Now, when I say that like this, it doesn't make a lot of sense. We'll go through examples, multiple examples, for you to see how this works. Conditional moment closure is very similar to this. It takes the original PDF, it writes it as a conditional PDF, and then solves for each component of it, for the PDF of psi r given psi m, and then for psi m. Now, this becomes very mathematically intense. There's not a possible way for me to talk about this in this class, okay? So I'm not going to discuss conditional moment closure or conditional source estimation. But if you're interested, come talk to me and I can tell you what is being done there. To me, I think the transport, my PhD was on transported PDF methods. So if I wanted to, I can talk about it for many, many hours. But this is not what we do now. We don't use transported PDF methods as much. In fact, most of combustion modeling that we do for LES relies on the manifold methods. And so it's a very powerful technique. It drastically reduces computational cost. And so it's a very useful thing to remember. And there are a lot of useful results that have come out of it. So in this class, the next 1 hour or so, we'll look only at the manifold methods. And if you want, I have slides on the transported PDF methods. You can go through them or we can talk about it. A conditional moment closure is separate. That's I can forward some papers that I have or the things that I wrote, but I don't have anything with me on hand to discuss this. Okay? So we'll look at mainly the manifold methods. So again, we are talking about diffusion flames first. You can do very similar ideas for premix flames also. The concepts are the same, so I don't have to go through each example to prove or to show how to do it. So we'll look only at diffusion flames. And if you understand how it works here, everything else is very similar. So we already discussed all of this, so you had questions on this. So all of this says exactly the same. So you want to use non-premix flames or diffusion flames because they're generally more stable. They have, they are less resistant, or let's say they're more safe, especially for aviation kind of applications. But there are also disadvantages. So locally, you can have very high temperatures. Even though the global fuel-to-air ratio might be low, locally you might have high temperatures that can create high NOx or emissions. And if you have inefficient mixing, like in an RQL combustor, where the rich region is too rich, you can form a lot of soot that may not get oxidized, and so you'll have soot emissions. So that's possible, yeah? So there are both advantages and disadvantages, but we want to look at diffusion flames. So I'll skip this part. I'll go to what I want to look at it here. So we looked at internal structure for premix flames yesterday when we discussed laminar velocity, laminar burning velocity, or laminar flame velocity, SL, right? So here, it's a little bit different. Candle is so that was a Bunsen burner that we looked at yesterday. So this is a candle, typical example for a diffusion flame. Candle works in a complex way. So it's not as simple as what I'd say this is here, right? It requires many different processes to happen together. But if I look at that specific region in the circle, and I look at what happens to oxidizer, fuel, and temperature, you will have a plot that looks like this. So fuel is coming from the inside near the candle wick. That's where the maximum fuel is. And as you go towards the edge of the flame, it's getting consumed. So fuel goes away. And then once you cross the flame, there should be no fuel typically, let's say. So that's why if you look at the fuel, the leftmost axis, the leftmost part of the axis is towards the wick of the candle. So that's why it has very high fuel. As you go towards the flame, it starts going down. Under the flame, it gets consumed, and then it's gone. Oxidizer, oxygen, is everywhere else. Air is outside in the room. So its maximum concentration is far away from the flame. So on the rightmost side, the blue line. And as you go towards the flame, it starts getting consumed. And of course, if you go towards the wick, there is no oxygen left. Everything has been consumed through the flame. The highest temperature, on the other hand, is neither close to the wick nor outside in the room, which will be deadly. If I light a candle and there the temperature becomes 1500 Kelvin, that's a bad idea. So it's only at the flame front, right? And so you get this peak in temperature. This is all there is to diffusion flame. There's not, we can think of a lot more complexities. But basically, this is it. And all we try to understand is that if you have a structure like this, what is it going to do in a practical application? Where is this flame going to sit? If I increase the velocity of the reactants, can I keep the flame lit, or is it going to extinguish? Right? Very important for aircraft engines. And if I don't burn this very efficiently, how much soot am I going to get? How much NOx am I going to get? So these are the main things I want to know. Okay? And so that's the fundamental flame structure. And then now from this, I have additional questions, especially a turbulent flame or things like that, where I change other conditions. So I'll skip this part. So the first part of trying to model diffusion flames is to split that psi vector into psi r and psi m. Okay? And for the most basic models we have for these kind of diffusion flames, that psi m turns out to be one variable or maybe two variables. That's it. So it doesn't matter how many species you have, that manifold variables can be only one or two. Okay? And this is typically referred to as the conserved scalar approach. Okay? So m here would be what is called mixture fraction. Okay? I don't know how many of you know what a mixture fraction is. Okay, only very few people. Mixture fraction is the most misunderstood concept in combustion, or not understood concept, because it's defined in a peculiar way, and then we lose track of what it is, and it makes no sense after all. So we all know what fuel-to-air ratio is, or equivalence ratio, right? If you want to think of it that way. So that tells you, for any given reaction, fuel and oxidizer, there's a particular combination in terms of mass for fuel and air that will ensure that both fuel and oxygen are completely consumed, and then you have products. So that's stoichiometric conditions, right? You can supply any amount of fuel, any amount of air. That's up to you as an engineer to figure out how much mass you want to flow into the system. And if you don't put in the right amount of fuel and air, you will have a different fuel-to-air ratio than what you need for stoichiometric conditions, right? So to tell someone else how you're designing the system, you use the variable equivalence ratio, which tells you what is the fuel-to-air ratio you supply compared to what is needed for stoichiometric condition. Okay? And if you say phi equal to 0.5, that tells me that phi equal to 1 is stoichiometric. Phi equal to 0.5 implies I'm feeding less fuel than what I need to burn all the oxygen. If phi is 1.5, then I'm feeding more fuel than what I need to burn the oxygen supply that I have, right? So that's equivalence ratio. Mixture fraction is no different. It's exactly like equivalence ratio. It's just defined a different way. And mixture fraction is normalized, which means it goes between 0 and 1. Phi, the equivalence ratio, is not normalized. If you have no air coming in, phi is infinity, which makes no sense. Okay? So you cannot treat variables like infinity in a PDE that easily. So mixture fraction allows you to keep it within 0 and 1. So it's just like mass fraction, so it's easier to solve. So you can think of it like a mixture fraction, some kind of normalized or renormalized equivalence ratio. Okay? So that's what you have for mixture fraction. So all of what we are going to do depends on the definition of mixture fraction and how we relate it to the reactive species. So this picture I took from Turbulent Combustion by Norbert Peters. So this is the definition of mixture fraction he has in that. So you have fuel coming in. We call it stream 1. That's where the fuel is coming in. And then around it, oxidizer is coming in. So you can think of it like a jet. So there's a jet on the ground, just a hole, like this one right here. Yeah? Can you guys see this from there? Now imagine fuel just coming out of this, right? So that's stream 1. Now, instead of having a cardboard around it, I could have another co-flowing cylinder or a pipe through which air comes out or oxidizer comes out. That I'll call stream 2. Yeah? So there's fuel that's stream 1, there's oxidizer that's stream 2. Okay? And mixture fraction is defined by this ratio. Now don't be confused or fooled by the definition there. Okay? So that's not exactly what we're going to use, but keep this in mind. It only depends on the ratio between how much fuel is coming in and what's the total mass that's flowing in, fuel plus oxidizer. You can also, you need to know what is stoichiometric conditions. So I need to know some basic equation to say, if I have this fuel, this is the amount of oxygen I would need to fully burn it off, right? So I write some kind of balance equation, simple one-step chemistry to find that equation. But what I do afterwards is the more critical thing. I take my species equations, y alpha, y1, y2, up through n, right? Out of this, I take my fuel, let's call it y1, the first variable, and oxidizer, let's say it's y2. The rest of it could be like carbon dioxide, all the intermediates, whatever else it might be. I take those two variables and I renormalize it in this way, okay? And if I do it the right way, using the one-step chemical equation that I showed you in the previous slide, if I do it the right way, I get a transport equation for mixture fraction, which is the bottom-most equation. And it tells me at any given location within the flow, what's the ratio between fuel and oxidizer mass fractions relative to some of the quantity that I have. So this is a partial differential equation, which means my mixture fraction is going to be different at different locations within the domain. So I can feed in some amount of fuel and oxidizer, and I can say there's 1 kilogram of fuel coming in, 5 kilograms of oxidizer coming in, and I can find an equivalence ratio. I can say I need 1 kilogram for oxidizer for every kilogram of fuel, but I'm feeding less, so you can find that ratio. That we call global equivalence ratio. That's not what I'm talking about here. Once I make this transformation for the species, I get a transport equation for mixture fraction. So at every point within the domain, I will have a different value for mixture fraction. So to look something like this. So this is an aircraft like combustor, an RQL model. Aircraft combustors are not rectangles, right? The cross-section is not a rectangle. So this is what you can study in a lab because if a curved surface it's hard to pass a laser through. So it's made into straight sections. So it's a model aircraft combustor. And if you look at it, there are many complex gadgetry to feed in fuel and oxidizer. But in the end, you get one small region through which fuel comes in and two concentric circles through which air comes in. And they'll come in, they react, whatever. They do things inside the normal engines should do. But what I can do is I can plot mixture fraction by solving that equation that I told you. And so that's an instantaneous picture. And this is the average time average picture within the geometry. And what you see is that very close to where the fuel comes in, that mixture fraction value is like 0.3 or something. It should really be 1, because when only it's pure fuel, it should be 1. But because we're doing CFD, there's some diffusion, things like this, so it's a little bit lower. So you see a max value of 0.3. And where oxygen comes in, that value is close to 0, okay, because there's no fuel there. So I've set up myself a scheme where wherever the fuel is being injected, I set the mixture fraction value at that boundary to be 1. Wherever oxidizer is being injected, I set the mixture fraction value to be 0. Okay? So when Z is 0, I imply the oxidizer stream, and when Z is 1, I imply the fuel stream. Okay? And when they mix, you're going to have values in between 0 and 1, and those tell you how much fuel and oxidizer are present at a given location. Okay? Now, this is a marker. You know, when the fuel and oxidizer go in, they're going to react. Okay? And if you've designed this properly, by the end of the domain, everything would have reacted. All the fuel is gone, all the oxidizer is gone if you're at stoichiometric condition overall. Okay? Mixture fraction does not care about it. If you look at the top, the mixture fraction is not 0, but it's close to like 0.1 or something like that. Okay? Mixture fraction only measures if there are no chemical reactions, how much of the fuel came from the fuel stream, how much of it came from the oxidizer stream to a particular location. It's measuring how much of those fluids came to any given location inside the domain. What happens after that, it has no indication of. Okay? So this is the important concept about mixture fraction. It tells you how fuel and oxidizer, when there's no reactions, how do they flow into this system? Okay, so it's a marker for the amount of fuel at any given location. Now, there's a stoichiometric mixture fraction, which is some value between 0 and 1. So I think for RP2 or endodecane or something like that, it will be like 0.06. That would be the stoichiometric mixture fraction for that fuel and air or air that's burning. If it's hydrogen, the stoichiometric mixture fraction will be very small. I forget what the number is, but it could be like 0.01 or some small value. Okay? So that tells you if you find within any given, in that domain, some value that's stoichiometric mixture fraction, at that location, the fuel to air ratio is the same as the stoichiometric fuel to air ratio. Okay? So that's what that tells you. So if I can solve this field, I now know at any given location from the inflow how much fuel and oxidizer have reached that location. Okay? So this is an estimation, this is a marker. So I will use this to do the rest of the modeling. So the simplest way to say, and this is an approximation, is to say whenever fuel and oxidizer reach a particular location, they immediately burn and reach equilibrium values. Okay? Which is a very stark approximation. This is not how the world works, but I'll make that assumption. So then what I do, I use Cantera or Chemkin or whatever. I take different mixture fraction values, different fuel to air ratios. I equilibrate that mixture. I find out what is going to be the temperature, what's going to be the product concentrations, all this stuff. And I store it in a table, in just, let's say, for lack of a better term, in an Excel spreadsheet. Okay? So I take mixture fraction value, and for every value between 0 and 1, let's say I take 100 values, like a grid of 100 values, I compute what is the temperature if I reach equilibrium with that mixture, and I store it. Okay? Now, when I do the simulation, all I'm going to do is to map that equilibrium solution directly onto the solution. So I will go to every point in the domain, that the picture I showed you, and I'm going to say, what is the mixture fraction? And I'm going to look up this Excel spreadsheet. Maybe for Z of 0.2, the temperature is 1200 Kelvin. So I just put that number in that cell, and now that's my temperature. Okay? So I have a one-to-one mapping between mixture fraction and the solution that I want, the species concentrations that I want. Because I've made an assumption that the reactions are so fast, they reach equilibrium instantaneously. That's the flame model that I've assumed. So if I do this, all I need is this mapping. Okay? Now, this is regardless of LES or anything like that. I can take DNS, I can write the DNS equation for mixer fraction, and I can solve the DNS equations, and at every point I get mixer fraction, I can find what that species value is going to be from my table. Okay? If you do LES, you have to do the extra step, right? Because you do not have the original DNS variables, you have only the LES variables. So instead of having Y, I need Y filter, and to get Y filter, I'm going to take that mapping, that table, and convolute it with the PDF for mixer fraction. So this is my manifold method. So instead of solving for all the species variables, I take mixer fraction as the psi m manifold variable, for which I prescribe a PDF at any given location in the domain. And g of z, which is the mapping function, I get it from separately solving equilibrium reactors in Cantera. If you use Cantera, that's what I would do, right? So I would solve that problem. So I pre-compute what will happen to reactions, I store it, and then when I run the calculations, I just look it up and I map it. So this is the easiest way to do it. So now I have completely reduced the complexity of the problem. Instead of solving 1,500 species in partial differential equations, I solve only for mixer fraction. The only equation I need is mixer fraction. And everything else comes out of this table. Okay? So this is the power of the manifold method. Because it's so simple to implement, it's been used, it's very popular. If you go to industry, this is like the most popular method for simulating aircraft engines. You can come up with all kinds of tools to simplify this mapping. You can run it very quickly. You can change fuels very quickly, and you don't need to change very much else in the simulation. So it's a very fast way to run different geometries, conditions, things like that. Okay? And the main advantage being that you only solve for the PDF of Z. Okay, that's the main thing. Okay. Now, the rest of it is all details, and it's not that critical at this point. So you can go through the details of how this PDF of mixer fraction is obtained and so on. So that's one angle of research. So some people claim that you can just fit it using a beta function, and others will say that you need to solve some complex equations to get the PDF of Z, things like this. The other angle of research is to find what is that mapping function. Right, so the G of Z. So here I said I use equilibrium solution. Of course, it's not correct because things don't react that fast. So we need to have some method to find what this G is going to look like. And different methods to find G will lead to different models. So you can have flamelet models. You can have flamelet progress variable approach, flamelet progress variable with adiabatic heat release. All of these different models come from how we approximate G. Okay? So these are the different methods. Okay? So let's not worry about P of Z anymore. That's, to me, not that critical. It's finding G that's the more exciting part for combustion modeling. Okay? So it's 3:05, 1 hour and 5 minutes. So let's take a break.